Hi everybody, welcome to lecture 15 of Electrical Engineering 331. In this lecture we will continue to discuss the frequency response. Remember that at the end of lecture 14 we were looking at, I called it a modified version of problem 230 in your text. Actually it'd be more accurate to say that it was just the first part of that problem. And in today's lecture, we'll look at not only the first part, but the second part as well. But first, let's confine our attention to the first part, which we began looking at in lecture 14 and will complete in this lecture. So what we talked about in lecture 14 was that we have an LTI system that's described by this differential equation, linear differential equation with constant coefficients given right here. And we were told that we have the input x of t, which is equal to cosine of omega t. And we wanted to find what the output would be if the value of omega is 2 radians per second. Now, what we said in lecture 14 was that the output y of t would be equal to h of the magnitude of h of 2 times this sinusoid with shifted by the phase of h of 2. So again, what we do is we'll just take this sinusoid right here that is the input, and we will multiply its magnitude. Now its magnitude or amplitude is just 1. We're going to multiply that by the magnitude of the frequency response at the frequency of interest. And then we're going to add to its phase the phase of the frequency response, again evaluated at the frequency of interest. So let's now see how this will go. Remember that we showed that based on this differential equation right here, the frequency response is given by this formula. And notice that we can find the frequency response at any omega using this formula. So in particular, we can find h at 2, which is what we need in order to finish this problem. And in fact, that's what it says here. All we need to do then is to use this equation for h of omega to calculate h of 2, and then once we get h of 2, which by the way will be a complex number, then we substitute that into this equation. We will substitute in the magnitude of h of 2 and the phase of h of 2 into this equation to find our desired y of t. So h of, and this should be 2 right here, not h of omega. H of omega, the formula for h of omega is right there, but what we want is this particular h of 2. So let me, this is just a little, basically a little typo there, that should be 2. So let me pause for just a moment and fix that. Okay, so now that's fixed. Again, this is the general formula for h of omega, but we're looking in particular for h of 2. So we stick in 2 for omega everywhere in this equation, and we will get h of 2 is equal to 5 times j times 2 over j times 2 quantity squared plus 2 times j times 2 plus 7. And so this is 10j over, when we square 2j, we'll get minus 4. So we have minus 4, and 2 times j times 2 is 4j, and then we bring over the 7, and of course 7 minus 4 is 3, so we have 10j over 3 plus 4j. Now, you can, I'm confident that you've learned ways to simplify expressions like this in the past when you have done complex arithmetic. But you know that sometimes that can that can be a little bit tedious. And so I want to show you a very easy way to go about evaluating expressions like this, and that is to go to wolframalpha.com. So again, what we're going to want is 10j over 3 plus 4j. And we're going to be able to use this website, wolframalpha.com, but we just need to remember to substitute I, and that can be lowercase I or uppercase I, it doesn't matter. Just substitute I for j. So 10j over 3 plus 4j. How will this go? Okay, so we'll go to the internet, and as I said, we want Wolfram wolframalpha.com, and we'll just say 10I divided by parentheses 3 plus 4I, and then hit return. And you can see what we have here. Right here, it repeats your input for you so that you can make sure that you have it correct. Now let's see here. Yeah, so it has the 10, and then this 10i, it put the I up here on top, but that's fine. That's still the same thing. And then 3 plus 4i in the bottom. So this input does match what we wanted. And here it gives us the result, 8/5 plus 6i over 5. And this is what is called the rectangular form. You could also change it to decimal, so 1.6 plus 1.2i, but this is still called the rectangular form of the complex number. And on the other hand, we also have information about the polar form right here. It is equal to magnitude of 2 and a phase of 36.87 degrees. And that, of course, is going to be particularly useful for us since we need to know the magnitude and phase to find y. And notice that it also even shows you the result in the complex plane. So this is really nice to know about, and it's absolutely free to you. Of course, some of you might have a calculator that will do complex arithmetic, and if so, that's great. You can use that. But this is a really nice resource to know about. So anyway, that's how you would use wolframalpha.com. So now returning to our discussion, as we just saw then, this number is equal to 8/5 plus 6/5, and now that I'm back in the notes, I've switched back to j. But you need to use I on Wolfram Alpha. Okay, just remember, wherever you have a j in your notes, use an I. So again, we found out that it is 8/5 plus 6/5 j, and as I said, that's kind of the rectangular form of the complex number. But what's more useful to us is this polar form, 2e to the j 36.87 degrees. 2 is the magnitude, or what Wolfram Alpha called the radius, and then this is the phase. And so we now know the magnitude and phase of h, so we can plug that in to this equation right here for y, and we get our final answer, 2 cosine of 2t plus 36.87 degrees. So you can see here we have multiplying that cosine of 2t, we have the magnitude of h of 2, and then the argument here has been shifted by the phase of h of 2. So it's just that simple to do these kinds of problems. So now let's look at another example. The next problem we will consider here is problem 230b. And we have it's the same setup. Remember, the problem we just finished was 230a. So here we have the same setup, but now instead of using omega equals 2, we are asked to find omega such that y of t is equal to a cosine of omega t, where a is some constant. Now remember, the input x of t, I just want to remind you, the input x of t here is cosine of omega t with no extra phase added. It's just omega t, cosine of omega t. And now we want to find out what omega should be in order for y of t to be a cosine omega t. So in other words, there's been no phase shift here. We started off with cosine omega t, we end up with cosine omega t, but with a possible magnitude change, but no phase change. So what omega will do that? So you can see that what we're really asking here is we need to find an omega such that the phase of h of omega is equal to 0. And again, how we know that is that there's been no change in the phase. The cosine of omega t was the input, a cosine of omega t is the output. There's no extra phase term there. So that means that the phase of h of omega is equal to 0. Now, how do we find the omega that will make that happen? Well, remember that we found that h of omega had this expression, which when we, now we have to keep it as omega. We can't substitute in 2 as we did before. We have to keep it as omega. So let's see, omega times j quantity squared is a minus omega squared. So we have 5j omega in the top, and in the denominator we have 7 minus omega squared is the real part. And then for the imaginary part, we have this j times 2 omega. Now again, what we want to do is to find an omega such that the phase of h of omega is equal to 0. So let's find an expression for the phase of h of omega. Okay, well, the phase of a complex number that's written as a fraction like this is equal to the phase of the numerator minus the phase of the denominator. So that's how I can write this. Now let's look at each one of these terms. Okay, again, this is the phase of h of omega, but this term right here, the phase of 5j omega, if omega is positive, that lies on the positive imaginary axis, and if omega is negative, it lies on the negative imaginary axis. So that means that the phase of this is plus or minus pi over 2, depending on whether the plus sign, we take the plus sign if omega is positive, and we take the negative sign if omega is negative. Okay, now what about the second term? Well, we bring down the minus sign, and then since the imaginary part is 2 omega, and the real part is 7 minus omega squared, then the phase of this is just the inverse tangent of 2 omega over 7 minus omega squared. And again, we want that phase to be equal to 0. So that's what we do, is we will set, oops, I dropped the plus or minus there, so once again, let me pause for just a moment to put that plus or minus there. Okay, so now the plus or minus is there where it should be. So we have plus or minus pi over 2 minus the inverse tangent of 2 omega over 7 minus omega squared is equal to 0. So obviously, that means that the inverse tangent of 2 omega over 7 minus omega squared is equal to plus or minus pi over 2. And to make the inverse tangent go to plus or minus pi over 2, we need for this term in here to be going to plus or minus infinity. And the way that we make that happen is by setting this denominator here equal to 0. So we have, that happens, of course, when omega squared is equal to 7. And there's two possibilities there that will make that happen, and that's omega equals plus or minus 7. And that corresponds to, we'll take, if omega's plus the square root of 7, then it will go to positive infinity, and we will get the positive pi over 2 here. And on the other hand, if omega is equal to negative square root of 7, then this will go to negative infinity, and that corresponds to negative pi over 2 here. So we get two possible answers, omega equals plus or minus square root of 7, that would, in either case, either one of those values of omega will give us y of t is equal to a cosine of omega t. So that's that problem. Now let's look at still another problem, and this one is problem 232 in your textbook. It says that a linear time invariant system has the impulse response h of t equals 5 e to the minus t u of t minus 16 e to the minus 2t u of t plus 13 e to the minus 3t u of t. That's the impulse response of the system under consideration. Now, it says if the input x of t is equal to 7 cosine of 2t plus 25 degrees, find the output y of t. Well, before we started learning about the frequency response, the only way we could have done a problem like this would have been to have convolved h of t with x of t. And if you're brave enough, I would definitely encourage you to try that. I think it would be an excellent exercise, but the problem is that this is going to be a pretty difficult integral because you're going to have to integrate by parts. So that's a tough way to go, and fortunately we have a much easier way that we can do this, and that is by observing the following. And here's something right here, this note in red is something that's very important. If the impulse response has the form e to the minus at u of t, then the frequency response corresponding to that is 1 over j omega plus a. So we just take each term, notice that each term in h of t has that form. This has that form with a is equal to 1. This has that form with a equals 2. And this has that form with a equals 3. And so, and we need to keep the right coefficients as well. But here we'll have 5. Let's see if I can make this a little smaller here. I'll fit on one screen. Okay, so 5 e to the minus t u of t then gives us 5 over j omega plus 1. Minus 16 e to the minus 2t u of t gives us minus 16 over j omega plus 2. And 13 e to the minus 3t u of t gives us 13 over j omega plus 3. And again, the coefficients give us the numerators, and the exponent of the e to the minus, or the exponent of e, helps us to determine the denominator. So this is the expression for the frequency response for this problem. Now, we want the frequency response at what frequency? Well, let's remind ourselves. It said x of t is equal to 7 cosine of 2t plus 25 degrees. So we want omega equals 2. And that's why I've drawn this line from there down to here. So we want h of 2. And so we just plug in 2 everywhere in this equation, 2 for omega. Go to Wolfram alpha, and believe it or not, when you plug in 2 there and everywhere and then plug this expression into Wolfram alpha, you get 0. H of 2 is exactly 0, which could be written as, if you wanted to get magnitude and phase, that's 0 magnitude e to the j 0 degrees. So y of t is equal to, now this is not 0.7, but this is 0 times 7, okay? 0 times, remember our input up here is 7 cosine of 2t plus 25 degrees. So here we have, down here, 7 cosine 2t plus 25 degrees, but then we have multiplied the magnitude of 7 by 0, which is the magnitude of h of 2, and then we have also, for the argument, we've shifted it by the phase of h of 2. But of course, 0 times 7 is 0, and so we just get y of t is equal to 0 in this case. And that happens because the frequency response at the frequency, this input right here is just a sinusoid of a single frequency, 2, and h, the frequency response at 2, happens to be 0, and so that's why the output is 0. I want to just emphasize, this input is certainly not 0. You can clearly see that's not the 0 function, but the output will be 0 because the frequency response at that frequency is 0. So let's do just a little bit more, and then we'll quit. We want to look at one problem here, just one remaining problem, and that's 229 part A. Now in 229 it says an LTI, linear time invariant system, has the frequency response function h of omega equals 1 over j omega 3. What is y of t if x of t is equal to 3 for all t? Now at first it may look like this problem doesn't fit in with what we've been doing, because we've been trying to find the response to a sinusoidal signal, but this signal is a constant. Like I say here, if x of t were a sinusoid, the problem would be easy. But note the following. X of t in this case is 3, but that's the same thing as 3 times the cosine of 0t. So this could actually be considered as a sinusoid of 0 frequency. And that's the key to doing this very easily. And so what we need to do then is we say, okay, since this is 3 cosine of 0t, then y of t will be the magnitude of h of 0 times 3 cosine of 0t plus the phase of h of 0. Okay, well, what about h of 0? Well, that's really easy, because if h of omega is 1 over j omega plus 3, then h of 0 is 1 over j 0 plus 3, which is 1/3, which is 1/3 e to the j 0 degrees. So that means the magnitude of h of 0 is 1/3, the phase of h of 0 is 0 degrees, and therefore y of t is equal to magnitude of h of 0, which is 1/3, times 3 cosine 0t plus the phase of h of 0, which is 0 degrees. And so 1/3 times 3 is 1, and then 0t plus 0 degrees is just 0. Cosine of 0 is 1. 1 times 1 is 1. So y of t is equal to 1 for all t. And that shows you how to do a problem of that type where you know the frequency response and you have a constant input. So as you can see, we can do some interesting things with the frequency response that would be much more difficult to do if we tried to do convolution. So that's it for lecture 15, and good luck.